Okay, so today we're going to be going over example 7.10, calculating out the packed height by the HTU method. We have 250 kilomoles per hour of saturated liquid feed of 40 mole percent isopropyl ether in isopropanol, being distilled in a packed column operating at 1 atmosphere to obtain a distillate or an XD of 75 mole percent isopropyl ether and a bottoms product of, or XB of 5% of isopropyl ether. The reflux ratio is given as 1.5 times the minimum, and the column has a total and partial reboiler, total condenser and partial reboiler. The mass transfer coefficients are given below, specifically here, which are for 6 values of x. We'll be using those to calculate out essentially a line. They have been given from empirical correlation shown in section 6.8, which is not exactly expressive of how they calculated them out, because they show numerous empirical correlations and how they're found and how they've been modified over time, but for me they didn't show anything specifically how to calculate them based on any data that they have given. So the way we start this problem is by essentially creating our vapor-liquid equilibrium curve and then adding in our operating lines. And so we can do that just like we've been doing before. This is essentially a blank that I have made that calculates out the rectifying line, the feed lines, and the stripping lines. It also calculates out the stages, but I have deleted those because we won't be using them for the most part. I mean, we will add in a reboiler. But then the isopropyl ether and isopropanol data was found from this paper, the vapor-liquid equilibrium and extractive distillation for separation of azeotrope isopropyl alcohol and diisopropyl ether. Diisopropyl ether is also known as isopropyl ether. It's one of the many names it has. And by taking this data, specifically the X1 and Y1 datas. And so that was here. You can see that the data is not exactly perfect, as in that it goes up. You can see part of the slopes. It actually has this little dip here where it's lower than you'd expect it to be. So while it's not perfect, it's the best that I could find, and if you guys want to use it, then I guess it's the best that you can find too. Okay. So the first thing we probably want to do, just because we're already right here, is to calculate out our L and our V, along with our L bar and our V bar. So our L is going to be basically just our distillate multiplied by our reflux ratio, which was 1.25, which is 1.5 times the R min. So if we actually change this to 0, it goes to the value I put in already, which is the R min. You can see that, yes, it does in fact seem to intersect with the line. So set this back to 1, goes back to our normal R1, or modified R min value, and multiply our R min by our D to get our L. Our V is going to be 1 plus the reflux ratio times our D. Our L bar was already found before, if you remember. It's just down there. It's what we use for our stripping section. And then our V bar is going to equal our V plus, this is going to end up being just our V because our Q is 1, but it is our v plus 1 minus our q times our feed. And that is going to be the same as it was before. Or L. Or V, sorry. Alright, so for the next part, we're going to essentially put in some more stages instead of all these. So we can pretty much delete all this. I'm going to leave one stage in because we'll be using one of them for the partial reboiler as a full stage. So we'll put that in starting from the bottom going up, which is going to be a little bit different from what we've done before. This will be essentially starting out our XB and then our XB. It looks like it's already trying to put our first stage in. If it doesn't, then you should go in and do your data ranges, go to add, this will be our reboiler, X values will be these, Y values will be these, and there it goes. So since we're going from the bottom and up, we're going to have to change this around. We're going to have the same X as before, so this will be the same X value that we had before. But our Y value is going to be based on our equilibrium curve. So we want to match our X to our liquid column to get what range our M's and B's are going to be in. These are actually going to be the same as before. Trying to get our M's and B's. So then we would be able to calculate out our Y value with this equilibrium curve equation where it's, well, I guess it's M times X plus B. So there you go, first line. And so now we're going to know what our Y is. It's going to be the same as before. And our value of X is going to be essentially an mx plus b based equation where you're solving for Y. So Y equals, or X, I'm sorry, X equals Y minus B all divided by M. So we have our stripping line equation, which represents, this would be your M and this would be your B, where it's negative. We'll take our B first and have our Y minus our B. So it's a negative, and we can change this to a positive. This will all be divided by our X value, which is right here. This is all going to be divided by our X value to get our value of X. So there you go. There's our first stage. So the next part would be to essentially use the Ka and Kya and Kxa values, our mass transfer coefficient, to solve for our specific y's and x's. So those values are here, Kya, Kxa. This would be for 0.15, 0.25, 0.35, 0.15, 0.25, 0.35, 0.45, I believe, 0.6 and 0.75. So these are our X values. Okay. I'm going to move these around a bit. So we want to essentially find our lines from these X values using this slope. So our slope would be negative Kxa divided by our Kya. And drag these down. So this will be for our stripping section, this will be our rectifying section. So we want to start at our X equals 0.15, so So this is where it gets a little tricky. We're going to essentially have our slopes intersecting our vapor liquid equilibrium curve. So we'll need to essentially have our slope where it intersects, specifically itself. So if we have our slope, we'll call that our M1. I'll just move this away. This will be our B. So M1, call this B1. And where this intersects our operating line will be different for each of these sections. So where our M intersects our B, we'll have our Y equals, well, we know what our Y is. So our rectifying section line, essentially evaluated, this will be our Y, evaluated at our X, and this is all Y equals, or B equals, minus our slope times our X value again. Okay, so we can write this down to the rest of our rectifying section, and then we can essentially do the same thing for our I'm sorry, I said stripping section. We need to do the same thing for our rectifying section using the rectifying equation. So our rectifying equation, this would be our Y. So with that, we're going to be multiplying by this. Y minus M times our X. Okay. So now that we have that, we can find what our intersect is. So for our intersect, we will have our equation of what our specific line is where it intersects. So to find the intersect, I don't think there's a specifically easy way to do it, but it is technically going to be like an index. We're going to have our, this is just one way to do it. That's a little bit tedious, but I think pretty much follows what we've been doing so far anyways, which has to do with a match and an index of what that match was. Unfortunately, since we don't know really anything about how to relate our value here to some value here on a line, much like the RD function, we're going to have to essentially guess a function that fits. So with this M, technically it's M2 and B2, we'll have to essentially guess what values and then fit them to make sure that they actually do fit. So we'll have to insert a line here to analyze it. So we have our index, we have our X values. I'm going to move these down. So we can have some space. So our X value is going to be where these intersect. So it's going to be the intersect equation, so we know our these y's will be the same. So if we're using mx plus b, or m1x plus b1, we're going to have the same y value as m2x b plus b2. So we're going to essentially do what our x equals with the same y's, although we don't necessarily know what they are yet, and we don't necessarily know if this is going to fit. We're going to put it in. We're going to see if it does intersect with the line. I'm guessing this is probably going to be right because I've already done this. But here we go. So we can do it either way. b1, let's say minus b2, right, divided by m2 minus m1. So 0.25, and then our y value. I'm going to move these over. This will just make more sense. Oops. There it goes. And this will be our y. This is going to be our rectifying line. So, or I'm sorry, I keep saying this, stripping line. So our stripping line is going to be right here. Yes, copy this, paste it here, change this. I've only done this like 20 times. Okay, that's our y. Then our x is going to be essentially our m times our x plus our b from our equilibrium line. Okay, so now we can go here, go to data ranges, gonna add a stage 1, I guess this would be, yeah, just call it stage, whatever, it doesn't really, it's not a stage, but it doesn't have to be. Okay, great, okay, well, I'm gonna make this a little bit easier to see. I don't know if that's big enough. But yes, it does intersect, so yay. So now we basically have our value of our intersect and then our interfacial area. So our value at a point and then our interfacial point, and then we can find our y minus our yi, which is pretty much what we want to do. Essentially we need to do this for each one of these, so we can make some room under each of these. And okay, so essentially we can just copy this down. These will all be the same. Well, this will change. Okay, so this cell here is basically all going to be the same as here, except with the different ky, kx, and x values. So I'm just going to put in these graphically and see how they turn out. So I added in the tie lines, as they're called. There's a few problems with it though. I forgot to add in the extra, the last one. So I'll just copy this over, paste it. We got our last one. And then the other problem is that this is for the stripping line, which we're not going to use. We're going to do it for the rectifying line. So we can copy this over. If you remember before, that it's a y equals mx plus b. So with this, I should be able to add it into here. Copy this down, paste it, should get it to where it needs to be. These actually all look pretty good based on where it's at right now, but just to make sure, you can change this to a smaller line, change all these, smaller line, make sure that it is in fact intersecting. Oops, that's the wrong one. I wish there was an easier way to do this. Yeah, this one looks a little bit off. Oh, come on, it's so small. Stage 6. Okay, so they are a little bit off. We can change these around a bit. So for the last one, let's try 10. Nope. Maybe 8. Maybe 9. Okay, that's right. And then this is probably going to be 10. I guess it doesn't really change. Okay, so these are the numbers that are specifically chosen for these stages. To find out where our values are. Alright, so what we really want to do is make a point of all these points. So if we take all of our x values, this is going to equal our, so this is for the line, this is the second part, so this is the x at where this is, and then this is going to be the original y value. And copy this down, or specifically do that for all of these. So this is the x for there, this would be the x for here, this would be the x for here, 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 and I guess that's all of them. And this would be the y values for these. We can plot them. So there's going to be two different ones, or not. I guess we can maybe plot it. We'll plot it as 2. So there's 6 stages, and this at the bottom. This would be our tie fit, I guess, for the stripping section specifically. For the stripping section, and then this is the y values. So we have a line. It's pretty much going through where these are. We can add a fit, a trend line. This can be linear, and we're going to have a equation and a coefficient. See how accurate it is. All right, so for our line, we're going to have a m of 1.366387. That should be enough. And then a b of 0.022643 5 should be enough. And then we can do it again. For the next one, let's be tie fit 2, I guess, for the rectifying section. This will be the rectifying section values. Alright, we can get a, we can click on it, tie fit 2, and insert trend line. It's going to be linear. We really just want the equation and the fit. So these are pretty linear. And this is going to be 0.5, 0.5, 44429. And this is going to be 0.34344249. Okay, so now we have a way of relating what our y prime, or sorry, yi to our specific y value, right? Cool. So since the kya values are lower than the kxa's, we're going to be doing an integral over our y values. So we'll start with where our integral will start, which is essentially right at the end of the reboiler. So our y value for our starting point is going to essentially be whatever the y value is at the end of our reboiler. So that's 0.167. So this is going to equal 0.167. The book uses various values across the board of 0.25, 0.35, 0.45, and then at the very end it's going to be where this line ends, so we can calculate that out as times 0.4, since we know that our feed line is at 0.4, that's where it's going to end, plus our b, so 0.567, it's going to be that. Call this feed value, or technically it's the end or the start. So for our rectifying section, this is all the stripping. Our rectifying section is going to start at the rectifying point, which is close but not exactly. These don't intersect like they are predicted to, but there's not a whole lot you can do. The rest of the values are 0.6, 0.65, 0.70, and 0.75. So we can find our x on our operating line. So our x is going to be calculated the same way as it was kind of previously, where we have our y. So we'll just calculate out our x by having our y minus m, or minus b, sorry. We'll just call this b for now. And then it's going to be divided by our m. Oops, it's just the m. So this is for the stripping line. Just take this. This will be our b. It's a negative. So we'll switch that in here. This is going to be a negative, so it's going to actually be a plus. And then we'll get our m and put that in here. Let's get our x. So 0.13 looks about right. So that's our x on the operating line. We can drag all this down to here. For here, it'll be our, similarly, this in parentheses minus our b divided by our m, and we'll just transpose our rectifying section values. This will be our m, or sorry, our b, and it is in fact a minus, and then our m will be our rd over rd plus 1. Okay, so our x for our operating or tie line, which is essentially from these equations, will be similar. We have, so as before, we'll be using our y value. This is our y value. It's going to be, we're going to use our slopes and intersects to calculate this out, and we're going to drag it down. So we're going to use our minus b. We're going to lock it in, and we're going to divide it by our m and lock that in. Okay, so I'm also going to do that here, except instead of our stripping section, we're going to use our rectifying section slope. And calculate out our x for our tie lines. So we'll have a y of the equilibrium curve I don't know why I capitalized that, but sure. We're going to actually need a value of m, our index M and a B. Just like before, we've been doing this, so we're going to take this, paste it here, and instead of matching our... No, actually, we're going to be using our tie line because that's where our x value is, so that's just kind of random and lucky. We want to match our x from our tie line that we just calculated to the x, so we can use our slope equation for the right spot. So that will be our m, well technically do it right, it's be m times our x plus b. Okay, so we have that, and that's not going to change, so we can copy all this down and delete these. Alright, so our yi minus our y is then going to be our, since we just calculated out what our x is for our yi, that's going to be our y of the equilibrium curve, and that's going to be also minus our y at the point before it moves. So when we took our y to be right here and our x to be right here, and we found our x value for when our y is using the slope equation from all of these, we get our y minus yi, and that's going to be pretty much the same all the way down. So now we just need our kya, and this is going to vary based on the values that they give, and they use interpolations. So the way that they did it was an interpolation, but you can't really do it this way using the interpolation. I'm not exactly sure how they do it. The way I would do it is, I guess, copy this stuff over. I'm just going to do it down here because it's out of the way. So like this. And here we go. It's going to be their x values. Then this is the kya for those values. I mean, this isn't going to be very accurate, but in all honesty, I don't really know how to do it any other way. So if we take these and plot them, where would that be? Where's the chart? Okay, so when I do a scatter plot, just do it like this. You can see that as it changes over these 3 points, there isn't really a real trend as far as I can tell. Can add a trend line. Just call it, just do a polynomial of 2. Of course it's going to have a perfect r squared because it's just going to fit that, but we do want the equation. So the equation is right there. We can also do the next one with the rectifying section. And this will probably be a little bit more accurate. And we just want an equation. So this is the equation for the x's of what their values of their ky were. So if we just use these equations based on our x's, so we have our x values, which is based on the operating line function, because that's where the k value is evaluated in the first place. So this will be, for the rectifying section, 2000 times our x for the operating line right here, this value pretty much, minus 850 times our x value, this is all from right here, plus 387.5. So the book has various values. For 0.25, it was 303. For 0.35, it was 300. For 0.20, it was 320. 5779 is a little bit different of a number, but they had 350, and this is 375. So these numbers aren't necessarily all that accurate, although their margin of error is pretty small since they're a few points off out of 300, which isn't the worst. So we can just continue on, and I can pretty much tell you that a few numbers differences in these won't really change the answer by too much. And I'll show you, I guess, once it's finished. So for here, we have our value of negative 66.6667 times our x. Oh, that did a linear interpolation. That is why it's so weird. Did not do the right. Oops. So the type, it's on linear. Should have done a polynomial. That was my bad. Okay, so the equation is negative 222.2 times our x from our operating line times x squared. Oops, that'd be x squared. Plus, just call 200 times our x plus 140. Okay. That is not right. I apologize, it's getting late. This is supposed to be a negative. There it goes. Okay, that makes more sense. There you go. Okay, so yeah, 184, it's not quite the same. 185, pretty close to 185 from the book. 182, this is also pretty close, so this is a lot more accurate. Okay. So the last part is going to be our integral, or not our integral, sorry. Our v over kya times our yi minus our y. And this is going to change based on what section we're in. So this is a v. This will be for the rectifying section. V, if it's in the stripping section, it'll be v bar. So we'll have our v bar from all the way up here, which we've already found. V bar divided by our specific value for ky, wherever that went. That's right here. Times our value of yi minus y. This doesn't actually need to be in parentheses, so this has already been calculated. Okay. So this is essentially going to be the same thing as before, except instead of the v bar up here, we're going to be using the regular value of v. Actually, it would be the same since it is q equals 1, so it's not going to change anything. It's weird. Okay. So we can check our values of here, of our sections, to the values they get in the book, which are here. We see that they had a 5.5, 5.4, 5.7, 7.4, 23. So we have a 7.7, 6.6, 7.7. So they're a little bit higher. For the stripping section, also a little bit higher. But that's just because our system is a little bit different. We're using different data. Our methods are probably going to have our different kya values and all this stuff. But we can do the trapezoid rule, or method technically, to figure out what our actual areas will be. So this is going to be our values added together, average technically, divided by 2, and then it's going to be multiplied by our the differences in our y values, since this is an integration over y. Oops, did I just pick the yi? That's so y, oh, and our y. So that's all over there. Oh, what? Why are you doing that? Okay, is this right? Yeah, okay. So I missed a parenthesis somewhere when I was deleting things, I think. I don't really remember. Okay, so we do that and drag it down. We don't need to do the last one because this one's already taking account for, oops, for both of these. So it already has, oh, I did it again. Has both of these accounted for. So we basically just have the summation of all of these. We sum these up. We get our value of 4.8, where they had a value of 3.6. It's really not too bad based on how this method calculates things out. For the stripping section, we're going to be doing the same thing. Actually, we can just copy all of this. I'll come out to 13.7, 12.3. It's much closer, probably because these values are more similar. If we actually use the book's values for their KAs, except for the endpoints where we actually did have to do something different, we can see that the values are not going to change dramatically. 320. So yeah, even with slightly different K values, the answers are going to be a little bit different, but not terribly. 82, 75, 165. So yeah, changed a little bit, not too much. Unfortunately, there's not a whole lot you can do without the actual empirical data, especially maybe for the curve. This curve data is also, like I mentioned before, not exactly the best. It's not refined just to be like a simple equation. It's got a lot of divots in it. But, you know, the method is pretty much what they use, so, except for the interpolations for the KY values. But there's not much else to do about it. And so there it is. Hope everyone has a good rest of the week, and I'll see you next class.